In this lecture, we'll talk about two kinds of interference that you can get from waves. One is constructive and destructive interference from two sources of waves. The other type is beat interference, which is used to tune instruments. So first, we'll look at the interference of two wave sources. Here's one wave source producing its familiar circular pattern of ripples. Now, what if I turn on another source next to it? Is that just going to amplify the waves that are produced? Well, not really. Here are two sources of waves on the surface of water. He's producing ripples from two balls that he's bouncing on the surface of the water. And notice that rather than amplifying the waves everywhere, instead there are actually dead zones that are produced where there are no waves felt at all. How can this happen? Turning on another source of waves actually kills off the waves in certain places and it amplifies them in other places. Overall, the energy is increased, but there are these dead zones with no wave at all. This has many useful applications. We'll talk much more about it later in the course, for example, with optics. One use of it you can visualize here is suppose you want to send a signal to the Hawaiian Islands, but you don't want the signal to be picked up nearby the islands. So instead of just sending out a single source of waves, that means everyone can pick it up around. You use two sources sending out the same radio signal, and you get a strong zone. You point that in the direction of Hawaii, and then you get a dead zone off to the side, so the neighbors to the island can't pick up the signal. So why does this happen? Why do we get these dead zones? How do we predict where they would be? The trick is to use the superposition principle. At any point out here, away from the sources, the amount of wave that you get there is equal to the sum of the two individual wave sources. So you can imagine just turning on source number one and look at the waves from source number one separately from source number two. You just have to add the two separate waves together to figure out what wave you're going to receive. Here is the pattern of dead zones, which are shown in blue. They're labeled with a number 0.5, 1.5, 2.5. We'll explain what that means in a minute. And then you notice right in the middle, there's that's a zone of strong waves marked with a 0. And then there's a zone over here of strong waves marked with a 1, and so on. What we want to do is explain, what do these numbers mean, 0 and a half and 1, and so on, and predict where these zones are going to be located. We'll do it more thoroughly later in the optics portion of the course. So the trick is to just look at the two sources separately. Just visualize first the waves from source number one, marked S1 here. We're measuring the waves here at this black dot. We just have to look at first the waves from number one, and we'll add to that the waves produced by number two. We don't have to have all of it together at once. Just take source one and add to it source two separately. So the trick is that the waves will be in step with each other at the measurement point, depending on how far the waves have to travel. In this example, the waves from source one travel 6.5 wavelengths to get to that point. The waves from source number two travel 7.5 wavelengths to get to that point. That means that when they arrive there, although the waves have traveled a different distance, there is the difference in path that they took amounts to just a wavelength path difference. So what's important is the path difference between the two sources. Not how far it is from number one and how far it is from number two, but the difference between those two values. You see, if the difference, like in this case, the path difference, which we often call delta, It means how far the waves from 2 traveled compared to the waves from number 1. If that happens to be, like in this case, 1 wavelength, or 2 wavelengths, or even 0 wavelengths, so we'd say in general it's m times lambda, where m can be 0, plus or minus 1, plus or minus 2, and so on. If the path difference is a multiple of a full wavelength, then the waves arrive in step with each other at the measurement point. And therefore, this will be in one of the strong zones where a large amplitude waves are measured. Notice the path itself is some kind of random number, in this case, 6.5 wavelengths. It doesn't matter how far x1 is. It doesn't matter how far x2 is. What matters is the difference in how far they travel. As long as the difference is, say, a full wavelength, then the waves are going to get to this point in step with each other. Because after a wavelength, the waves are back in step. And they're peak upon peak, trough upon trough, and the waves are amplified at that location. This is what we call constructive interference, where the waves are lining up. It's different from harmonics or resonances on a string. In that case, you had waves going to the right and to the left. And sometimes the waves lined up on each other and you got a big wave out of it. Sometimes the waves canceled off and the standing wave was flat. That's not what's happening here. The waves are always lined up at this place and you get a large amplitude wave there. Now, instead, what if the waves are out of step? They're not a wavelength. If they're differing by a wavelength, they're effectively lined up with each other when they get to the measurement point. But what if they're not lined up? How can that happen? Well, in other words, how could you arrange it so that the trough of wave number 1 hits the peak of wave number 2? That happens when the waves are shifted from each other by half of a wavelength. Remember, this is a full wavelength. So in this case, you've got peak upon peak and trough upon trough. That happens when they're lined up with each other. Now, how would I arrange it so that it's peak upon trough? Well, I have to shift one of them over so that it's shifted over by half a wavelength. That's half of a wavelength of shift. Now, it also could be 1.5 wavelengths or 2.5 wavelengths, and that will put them out of step, and they'll cancel off at the measurement point instead. So this will happen when the path difference, 2 minus 1, is equal to half, 1.5, 2.5, and so on. And so we'll write that as m plus a half times a wavelength, where again, m can be 0, plus or minus 1, plus or minus 2, and so on. So the values of the integer is the same, but the equation's different. It's a half or 1.5, and so on. This is what we call destructive interference. And again, it's not like resonance or standing waves, where sometimes the waves destroy each other, sometimes they amplify each other. At this point right here, it's a dead zone. There are no waves measured there whatsoever, just like what we saw here. There are places where it's absolute stillness, no wave at all. So this isn't resonance that we're talking about here. Okay, so that's pretty much it. We can predict exactly where the waves will amplify each other if the path difference is m times lambda, and we can predict where the waves will cancel each other off if it's m plus a half times lambda. By the way, notice how it's always plus or minus 1. It could be minus 1 if you're closer to source number 2. Then you see 2 minus 1 would be a negative number. And so plus or minus integers are perfectly sensible here. Okay, so let's look at an example. Two identical loudspeakers are driven in phase by a common oscillator. Decipher this for a second. They're driven in phase. That means the speaker moves out at the same moment for both speakers. They're not out of phase, like they're not pushing and pulling opposite each other. The speakers are moving in phase, just like on the water, he was pushing the balls against the surface in phase with each other. And they're driven by a common oscillator, 800 hertz. It means they're both going at the same frequency. If they don't go at the same frequency, the wavelengths are different from the two sources, and you won't get those dead zones, and the effect doesn't occur. Okay, so we've got the two speakers facing each other. So it's the two sources, source number one and source number two. They're facing each other, and we're looking at the points along the line where there's minima of sound pressure. In other words, where are the dead zones? The destructive interference locations along the x-axis here. Okay, so here's the x-axis, and I want to figure out where the dead zones occur. I'll call the position x, which means that what I'm saying is x1 I'm calling x. The distance from speaker 1 I'm calling x. The distance from speaker 2, of course, also matters. How far away are you from speaker 2? Well, it would be 1.25 meters minus x, just the remaining distance. Okay, so to locate the minima means you're talking about destructive interference. We're looking for the places where the path difference, which is x2 minus x1, which I can simplify. X2 minus x1 comes out to be 1.25 minus 2x, plugging in the two values for x1 and 2. Destructive interference will happen when that path difference is equal to m plus a half lambda. And we're going to have both positive and negative m values because some of them are going to be closer to source 1, some of them would be closer to source number 2. So you'll have both positive and negative path differences to look for. So what we have to do is just start plugging in values for m and see what we can find. So m equals 0. First of all, in this case, m equals 0 is not going to be, sorry, not true. I'll start at 0. I'll start at m equals 0 and see what values of x I find. Notice what I'm going to do here is I'll plug in m equals 0 and solve for x. So now we'll just solve for x, and then we'll interpret the results here. So I'll solve for x, and what I find is that x is equal to 1.25 over 2. That's the center point, right in the middle. And then minus m plus a half times lambda over 2. So the idea is I'll plug in the different m values, 0, plus or minus 1, plus or minus 2, and so on, and locate all the positions of destructive interference. Before we do it, let me decipher this a little bit. This is the center point, 1.25 over 2. For m equals 0, this number is a half. For m equals minus 1, this number is minus a half. So notice what you get is you get the center point plus or minus 2 points on either side of it that correspond to m equals 0 and m equals minus 1, which corresponds to the values of plus or minus a half. So let me write these down. For plus or minus 1/2, I get the values of x which are just to the left and to the right of the center point. They're at 0.52 and at 0.73. Okay, then next I can look at the plus or minus 3/2 values. Plus 3/2 corresponds to m equals 1, and so on. So plus or minus 3/2, meaning these are the 2 points which are have a path difference of 1.5 wavelengths, 3/2 of a wavelength. The two values there come out to be about 0.3 and 0.9. And then there's one more set, which is plus or minus 5/2. And the values there are about 0.09 and 1.2. That's it. Notice how they come in pairs. You see, at the exact center point, the path difference is 0. So at the exact center, you would get waves arriving in phase with each other from the two, and that'd be a loud position right in the middle. But as you move off to either side, you're going to get to a point where there's half a wavelength of path difference on either side of the center, and those are these two values. And then further out, another pair, and then further out, finally one more pair, and then that's it. Those are all the points that are between the two speakers. Now, before you try to set this up, in principle, you just have two speakers, a stereo pair of speakers, and sit between them, and you could find these dead zones. It won't really work well because you're going to get a lot of echoes from the walls. So you'd need like a chamber, an anechoic chamber that has padded walls so you get no echoes that mess up the effect. It's hard to demonstrate it with sound waves, but it's easy to do with optics. You can have two lasers and have points where they cancel each other off in between. By the way, why didn't we treat it like standing waves? Don't we have a left and a right moving wave, and we could figure out where the node locations are? Aren't those the destructive points? Not in this case. Standing waves happen when you have waves reflecting off the boundaries, and the boundaries determine what the waves look like at the ends. For example, a string fixed at both ends, the ends of the string must be nodes, and that lets you locate the node locations every half wavelength along the string. That is not what's happening here. The ends here at 1 and 2 are not required to be nodes or antinodes or whatever. There are no special boundary conditions that enforce the shape of a standing wave that's produced. So it's not a standing wave situation. It is a constructive, destructive interference from just two sources, and that's how we solve the problem. Now we have two speakers again, but now we're looking at the points not between the two speakers, but out in front of one of the speakers. And we want to find the points of destructive and constructive interference again. In this case, we're supposed to assume the speed of sound is 344. So the wavelength of the sound waves, it all hinges on the wavelength, right? How the path difference relates to the wavelength. The wavelength is the speed 344 divided by the frequency of 784. It gives me a wavelength which is 0.439 meters. Okay, so as usual in these problems, what matters is the path difference that the waves take. From speaker number 1, speaker A, that's this path, which is the hypotenuse of a right triangle here. This is x. This distance is x2, which is, by Pythagorean theorem, equal to the square root of x squared plus 2 squared, or 4. So the path difference, which is what I care about, The path difference, delta, is x2 minus 1, or xa minus b, and it's equal to the square root of x squared plus 4, that quantity minus x. That's our path difference. As usual, if that is equal to, say, half of a wavelength, then you're located at a point where the waves cancel each other. Okay, and in fact, since in this question we care about both destructive and constructive locations, it'll be useful to set it equal not to m lambda or m plus a half lambda, but let's be general about it and just say it's equal to some number beta times lambda. That way, constructive interference means that beta, I can plug in beta values which are 0, plus or minus 1, and so on. And if I want to solve for the destructive points, I'll set beta equal to plus or minus a half, plus or minus 3/2, and so on. That way I just kind of get one equation for all the different possibilities. So let me do that. I have to solve this equation for x. As it's written, it looks pretty ugly, but if you just bring the x over to the right and then square both sides, it just gets rid of gets rid of all the square root, and it simplifies down nicely. So just rearrange it, and you'll have on the left x squared plus 4, and on the right x plus beta lambda quantity squared. The x squared terms will actually cancel. You don't even have a quadratic equation. Write down the algebra and you see what I mean. And you just get a simple equation for x. X is just equal to 4 over 2 beta lambda, which simplifies. I'm not sure why I didn't simplify it. It's just 2 over beta times lambda minus beta times lambda over 2. We can plug in whatever values of beta, it'll locate the constructive and the destructive points. Okay, so if I want to find the destructive positions, or let's start with constructive first. Constructive, beta equals 0. Where does beta equal 0? I mean, yeah, where is beta equal to 0? Well, this term cancels off, but I'm dividing by 0 here. It implies x equals infinity. What does that mean? That means the place where the waves are in step with each other, where the path difference is actually 0, is at infinite distance in front of it. That should make sense because, even right up to speaker B, there's a path difference. The further out you go, the less of a path difference there actually is. Now, the actual path is very far when you're far away from the speakers, but the difference in path approaches 0 the further away you get. You can check that, let x go to infinity in the expression for delta, and sure enough, the path difference is 0 as you head way far away from it. Okay, so there really is no point where the path difference is 0, but I can let beta equal 1 and find a point there which is 4.3 meters. And then let beta equal 2, and I get x equals 1.8 meters. Notice that as you get closer to the speakers, that's where the path difference is actually greater. Like when you're only 1.8 meters in front of it, that's where the path difference is 2 wavelengths. That should again make sense because as you get closer and closer to the speaker, although the paths are shorter, the difference in the paths becomes more extreme as you get closer to the speakers. Notice in front of speaker B, that's when the path difference is actually biggest. As you go further and further, the path differences are comparable to each other. Okay, that's how you locate the constructive points. Same deal to locate the destructive interference locations. For instance, if I want to locate uh, beta equals a half, that's the place where they're a half wavelength out of step. By the way, in this case, the negative values are not meaningful. Like beta equals -1, that would mean you're closer to speaker A, which is not the situation here. You're definitely closer to B. Only the positive values make sense in this problem. So beta equals 1/2, that's actually very far away. When they're a half wavelength path difference, that's actually very far from the speakers at about 9 meters. Beta equals 3/2 is closer to the speakers, 2.7 meters, and so on. That way you can locate all the points that you want in front of the speakers. Now let's look at question C. If the frequency is low enough, there'll be no positions at which destructive interference occurs. No positions along this line, that is, along which there's no destructive interference. How low must the frequency be? Now, remember, there's no path difference when you're super far away. As you get closer and closer, the path difference grows. You only get destructive interference when the path difference grows to be half of a wavelength. So it's possible that as you get closer and closer and closer, the path difference might not even become half a wavelength in size, and then there'll be no destructive points. In fact, the biggest path difference that's possible is 2 meters. Delta max, the maximum value of path difference possible here is exactly 2 meters. 2.00 meters. And if that's equal to half a wavelength, then that would be that would give you the maximum wavelength where you're only going to get one destructive interference, which is just right in front of the speakers. You stand right in front of B, and 2 meters happens to be half a wavelength, then the waves actually cancel each other out, and you won't hear anything at that point. Kind of weird, you're sitting right in front of a speaker, but no sound is heard by you, just because the waves are canceling each other out. So that means lambda is going to be 4 meters. In this, that's the lambda max value. And that lets you find the frequency, the low frequency that's needed. F would be 344 meters per second divided by 4 meters, which gives a frequency of 86 hertz. Any lower than that and the wavelength's too long, and even when you're right up to speaker B, still the waves aren't half a wavelength out of step. It might be helpful to look at the picture we saw before, this one. We have the two sources, and we're here on this line out in front of speaker number 2 in this picture. Okay, so way out here at infinity, there's 0 path difference. Then as you get closer and closer, you cross the m equals half, or we called it beta. We called it beta equals a half line. Then you cross the m equals 1, then the 1.5, then the 2, and then the 2.5 line, and so on. So again, as you get closer, the path difference is actually greater. Way out here, although the path is bigger, the paths are bigger, the difference in path is not. But the path difference actually gets larger as you approach the speaker.